In the following diffraction pattern, A, name the order of maximum or minimum at A, B, and C. So we have diffraction pattern given in the question. So let us discuss the solution of question A, okay? We need to name the order of maximum or minimum at A, B, and C. So we can see in this diffraction pattern, A corresponds to central, okay, maximum, or it is also called principal maxima, okay, and the order for central maximum. So I'm writing the order for central maximum, okay, maximum, that is in this question, okay, A corresponds to central maximum is n equals 0. So we have this is to be noted, okay, and B corresponds to first order minima, okay, it corresponds to first order minima. So the order for B is n equals 1. So we have this. Clear? Next, C corresponds to, okay, so I'm writing over here. C corresponds to first order, okay, maxima or maximum, and the order for C, so I'm writing over here, the order for C is n equals 1. So we have this. Clear? For question A. Now, sorry, let us go for solution of question B. What is the linear distance and angular distance between X and Y? So we can see Y, okay, is at this position. So we need to find angle corresponding to Y. Okay, so I'm writing over here. C corresponds to first order maximum. So that is n equals 1. Clear? And we know the standard formula, okay? We know the direction of secondary maximum. So I'm writing over here. Direction of secondary maximum, and we can see secondary maximum in this diffraction pattern corresponds to CD, okay? We can see CD corresponds to secondary maximum, is given by this equation or relation d sine theta equals 2n plus 1 lambda by 2 and n equals 1, 2, 3, so on. Okay. Now what do we find? If sine theta is approximately equals to theta, then we can write d times theta. Okay. So this equals 2n plus 1 lambda by 2. Therefore, we can write theta equals 2n plus 1, okay, lambda by 2d. So we have this relation, okay? We have this relation, okay? And we can also write in this way, theta equals plus minus 2n plus 1 lambda by 2d, okay? So right now, I'm simply writing in this way. So this is to be noted, okay? For secondary, minimum, we have theta equals n times lambda by 2, or we can write theta equals plus minus n lambda by 2. Okay, so we need to note this. Clear? So we have this. So let me write in this way right now. So we have this relation, and we need to note one thing. Okay, we need to note one thing. N equals 0 corresponds to central maxima or maximum. So let me write over here. N equals 0 corresponds to central maximum. So this is very important, okay, concept. So we have this. Now, to find linear distance, okay, and angular distance between x and y, we need to find theta, okay, corresponding to y. So we need to find theta corresponding to y. So let theta corresponding to y be theta y, okay? So we have this. So that is, we have to determine theta y, okay? So we need to find this. Now, in order to determine theta y, we use this equation or concept, okay, as I said earlier, for secondary maximum, theta equals 2n plus 1 lambda by 2d, and n equals 1, 2, 3, so on. So we are going to use this concept, okay? So I'm writing over here. This is the concept we are going to use. And we can see in this diffraction pattern, C corresponds to secondary maximum of first order, okay? So as we discussed earlier, C corresponds to first order maximum. So C corresponds to secondary maximum of first order, and D corresponds to secondary maximum of second order. So we need to understand in this way, okay? So we can write in this way, okay? Take n equals 1. So we have to take n equals 1. We have theta y equals 2 times 1 plus 1 times lambda by 2d. Okay, so we have this. So we get theta y equals 3 lambda by 2d. So we have this. So finally, we get theta y, okay, or we have obtained theta y. Now, we need to find the angular separation, okay, between x and y. So we need to find this. So let the angular separation be delta theta, okay. So I'm writing over here, angular separation between x and y, clear? That is central maximum and first order maximum, okay? First order maximum is delta theta equals theta y minus theta. So we can find in this diffraction pattern theta equals 0 for x, and we have obtained theta y equals 3 lambda by twice d. Therefore, we have 3 lambda by twice d minus 0. Therefore, angular separation delta theta equals 3 lambda by twice d. So we have this. Okay? We have this. Now, to find linear distance, okay, we are going to find the linear distance. So to find linear distance between x and y, now what we do is that, okay, we use this equation or we use this concept. Let's say the linear distance between x and y is this, okay. Let's say this is x, the linear distance, okay. So what is this? This is linear distance. Okay. Now, since x corresponds to central maxima, okay, or central maximum, so for y, okay, in the diffraction pattern, we have this, okay, or we are going to use this equation, okay, d sine theta, this equals 2n plus 1 lambda by 2, and we can write in this way d, and we use this concept, okay, sine theta, this is x by d. So we need to understand the theory for finding the width of central maxima or maximum, okay, and from the theory of finding the width of central maximum, okay, we solve this numerical or we solve this question, okay, related to that. So we have sine theta equals x by d. So this equals, and we have n equals 1, okay, for y. Therefore, on putting n equals 1 in this side, we get 3 lambda by 2. So we have this. Sorry. Therefore, x equals 3 lambda d by twice d. So this is the linear, okay, distance. So we have this, or alternatively, we can solve in this way also, okay? Alternative method, okay? We use this concept, linear distance between x and y equals angular separation, okay? Angular separation between x and y times d. So we have this, and we know angular separation is 3 lambda by twice d. So we have capital D, okay? Therefore, linear distance equals 3 lambda d by twice d. So we can use this concept directly in order to find the linear distance between x and y. So we have this. So solution for C, okay? We can see in this figure, okay? This is secondary maxima and this is also secondary maxima. So this corresponds to n equals 1 and this corresponds to n equals 2, okay? So these are secondary maximum. So from question, okay, we have what difference is there in the angular position and intensity. So we have just found theta y. So theta y equals 3 lambda by twice d. So this is 3 lambda by twice d. Now let us find angular position corresponding to d, okay? So corresponding to this position. Now let the angle corresponding to this position be theta d. So we have this. So I'm writing d corresponds, okay, corresponds to second order maximum. So I'm writing in this way, second order maximum, that is n equals 2. So we have this, and we are going to use this equation, okay, d sine theta, or let me write directly, okay, theta equals, okay, 2n plus 1 lambda by twice d. So this is for secondary maximum, okay? So we are going to use this concept and we have n equals 1, 2, 3, okay, so on. So I'm going to use this relation. So we can write theta d equals 2 times 2 plus 1, okay, and we have lambda by twice d. So theta d equals, on simplification, we get 5 lambda by 2d. So we have this. So angle corresponding to d, okay, so this is, so let me write over here, this corresponds to 5 lambda by 2d. So we find this, okay. So what we find, we can see when we move in this direction. So what do you find? As the angular position increases, okay, as the angular position increases, intensity, okay, intensity goes on decreasing. So I'm writing over here, as angular position, that is theta, okay, increase or increases, intensity decreases. So we have this, okay, for solution of question C.